I think everything is fine. So just I'll spend around a few minutes to discuss what we have discussed in the previous class. So one is the pure metal. Pure metals are not strong, not having the properties which is required for the engineering application. Let it be engineering application. To get the better properties, you have to go for alloying. So when you're going for alloying element,
So your
hello, any difficulties? Any difficulties? Technical issues? Okay, everything is fine, I think. Yes or no? Visible and audible?
Yes, and now it's audible.
Okay. So you are talking about the pure metals, but pure metals we don't get the required properties that is expected for a particular engineering application or any application. For that, you have to add alloying element. So you are talking about the imperfection. Imperfection is related to microscopic level, not defect in the macroscopic level. So when you add alloying element, it will become impure. We can say that it's very simple. You have pure metal, you are adding alloying element. So when you're adding alloying element, it will become impure. Instead of saying impure, you are saying, so there is a imperfection in the crystallographic level. Now when you have to better to use, when you're answering the question also, you have to use the correct technical term. So then you can score good marks. So there is a instead of impure, so you are going for the imperfection in the crystallographic level. It happens. So it may happen in different level. It may happen in different level. That so then other than that, there is a one more term you have discussed is the phase. Before going for the phase, we have the grain. This is one grain. You should be able to differentiate between the grain and phase. Now, in the till previous class, we were discussing about only grain. The complete module 2 and module 3, you are talking about the phase. You studied the liquid phase, gaseous phase, as well as solid phase. But when you come to material science, you are not discussing much about liquid phase. You are not much discussing about gaseous phase. You are talking only about the solid phase. Within the solid, there are many phases are there. Those things you have to understand. What is phase? You have to define it properly. All those things are comes under module 2. That's the fundamental. Now one is grain. The grain already we have studied. Grain consists of many unit cells. So finally, unit cell will join together and finally it forms grain. Then, so this now dark space, we can hear one is dark region, one more is white region. What diagram you are shown here, it is only the schematic representation. It is only the schematic to understand the concept. So you are shown the schematic representation. This is the actual photograph. I think this is again from a Callister textbook. This is actual photograph and showing white region and background the dark region. Within the white region, we can see here. So this is one region, this is one more grain, this is one more grain, this is one more grain. Grain is not, don't think it's always it is circular, it's having irregular shape. But some cases you are assuming that it is almost circular. In general, if you see this diagram, there are two phases we can say. One is dark phase and one more is white phase. Within the white phase, there are number of grains. This is white, this is one grain, this is one more grain, this is one more grain. In the white space itself, phase itself, there are many grains. The dark region or dark phase, again, it consists of many grains. Now, there are many grains. If you once you say phase, there are many grain, but those grain having a similar properties. Imagine this is one grain. I think hope you can see the photo. This is one white grain. This is one more white grain. This is one more white grain. This is one more white grain, almost white. So these grains having similar physical properties, mechanical properties, electrical properties, or chemical properties compared to the dark region grain. This is one grain, the dark grain. This is white grain. If you consider physical properties, mechanical properties, thermal properties, electrical properties, those properties are different for white grain as well as dark grain. That is very, very important concept you have to understand. We have grain. The grain, there are many grains of similar properties. And when you take the photograph, micro photograph, by using a special microscope, high resolution microscope, we can see those grains. So the grains may be almost similar color. In this case, it's a white. Is a one the phase, and this white phase consists of many grains. Now I think you can start from atom. Atom joined together, it forms unit cell. Unit cell joined together, it forms a grain. And if there are many, the grain of similar properties and similar structure, so they may those group of the grains having similar properties or similar structure are referred as a phase now. The phase is having different physical properties, chemical properties. There are two phases here. I think it is clearly visible. One is dark phase and one more is white phase. The dark phase having different properties and white phase is having different properties. If you know that, we can go ahead now. So now I always use technical terms. So we are talking about not just defect. It is these are the what discussion you are talking about only the crystalline defect, not macroscopic defect. So you are talking about the lattice irregularities. You have to use the term in the writing the examination. Lattice irregularities, crystalline defect. So those terms you have to use when you explaining this. There is if there is only one atoms are missing or only few atoms are missing, those will come under point defect. Point means one atom is missed one place, then it is referred to the point defect. Suppose one student is absent in the physical classroom, there is one vacancy is there, that is nothing but a vacancy. If you have interstitial atom, your class number of benches strength, number of benches may be 25 into 2 means 50, so only 50 can be accommodated. If we add one more person, he may stand somewhere at the in between, then it will become interstitial atom. Example for the interstitial atom is carbon in iron, in steel. Fe is one main atom. The carbon atom is there in steel. That is referred as an interstitial atom. So vacancy may be created during solidification process itself, or during your crystallographic, during crystallization process, or solidification process, or during casting process itself. Then there is one more substitutional atoms. So where one atom is substituted by another atom. I am giving simple cubic. There is one carbon atom like a copper and nickel. So if you add nickel, this copper atom from the particular corner is substituted by nickel atom. Imagine your 50 strength of the class is 50. So one student will give the space for one more extra guest. Like one guest is coming to your class, so he'll get up and he'll give the space for the guest. In the similar way, so one atom is substituted by another atom, or parent atom is substituted by the allying atom, or solvent atom is substituted by solute atom. Those are the terms you have to use. Don't give the class example. Don't explain, just to understand I explain. So your then one more type of defect is line defect. Line defect is also referred as a dislocation. When group of atoms are missing from the some edge, then it is referred as line defect. There is a grain boundary. Those are the area defect. The point defect already we have discussed. Vacancy, one atom is missing. Self interstitials. So we have regular atomic structure. Let it be simple cubic. All corner one atoms are there. So one more additional atom is entered and occupies some BCC at a body-centered position or some other position. Then it is referred as a self interstitial. Imagine we have only Fe. We have Fe is a BCC structure. All corner one atom, and in the center there is one more atom. If one more Fe atom goes inside the unit cell and occupies at certain position, then it is referred to self interstitial. The parent atom as well as interstitial atoms are same, then it is referred as self interstitial. Suppose carbon atom goes and occupies at some spaces in between the lattice, then it will not become interstitial, no, self-interstitial, it is just interstitial. The example for interstitial solid solution is carbon in Fe, because complete second module is based on this concept. That's why I'm repeating. If you read the book, you require more time. First you understand, so don't miss the classes. Then you can read any books. That's your choice. So alloying, so once you add alloying element, it is referred as the impurity itself. So that is referred as imperfection. So we are adding alloying element. There is a point defect in alloy. So here you can see. So one atom, we have black circles, and one more is orange circle. These are orange color. So that is reddish color. So these black circles are replaced by black atoms are replaced by some color, reddish colored atom. That is nothing but a substitutional solid solution. It is one is schematic sketch, copper in nickel. So that means major alloying element is nickel. The copper atoms you can hear. You can see this reddish color. Those are the copper atom. Interstitial also you can see here. These are the schematic sketches are available in Punish textbook. You can refer. You can practice. Like Fe, the dark atoms are Fe. These colored atoms are the carbon. The carbon occupies interstitial spaces in iron in its cell or BCC in its cell. These are the rules. I think I'm not going to the rules already you are discussed. Now you have to require this part. Hope till now I think you don't have any doubt. If you have the doubt, you can clarify. I'm going for the one more topic. It is a little bit hard to understand, but you can understand easily. Next is dislocation. In mechanics of material you are studying, you are applying certain amount of load. Let it be 10 kN. You have steel rod, you are applying 10 kN load. The material will be elongated by 1 mm or 2 mm. Let it be original dimension is 100 mm. It is elongated by 0.1 mm. So that is in the macroscopic level. We can physically measure the initial length and final length. You can compare and you can write the total elongation is so 100.01 is the final dimension. The initial dimension is 100 mm. Net deformation is 0.1 mm. Like that you can write. That is in the macroscopic level. But in the microscopic level, how elongation takes place? We are applied force. It elongates. Everyone knows. But being a material scientist or material engineer, now we are normally mechanical engineer also. The literature we can say that material engineer, we have knowledge of material engineer. Material scientist, normally those who are doing master degree in materials, there is a separate division, separate master degree in materials. Even NITK, they have materials, master degree in materials, PG course in materials. They have undergraduate course, 4-year course only on material science. Here you are studying one subject, but there is an undergraduate course only on material science. Then master degree course only on material science. Even Indian Institute of Science, there are many divisions. Material research division, there are many 2 to 3 divisions are there. They are working only on materials only. But as a material engineer, we should know what is happening inside the material, how it is elongated. So what is happening in the grain level, what is happening in the even the phase level, what is happening in the lattice level, all those things you have to understand then for getting plastic deformation. So one is dislocation. Once you say dislocation, it's a line defect. One is point defect. The next level of defect is higher order defect is line defect. Or in simple way, we can say that the group of atoms in the line or one line of the atom is missing. Imagine we have especially schools. Imagine there are 3 rows of the students standing during the celebration of Republic Day. If one line of the students is moved away from the gathering, then it is referred as a dislocation or line defect. One complete line of the students, they are leaving the area. But here the one line of the atoms or group of the atom, it is on the line, are moved from one lattice to one crystal to another crystal. You have to use the correct term. In the lattice structure, one group of the atoms are moved from one crystal to the another crystal. Not only one atom. If only one atom is moved, then it will become vacancy. If a group of atoms, those atoms are in the line or edges, those are moving from one location of the lattice structure to the another location or in the grain, then it is referred as a dislocation or a line defect. Now, if you go according to the terms used here, the dislocations are line defect that already are discussed. Now, important term is slip between crystal plane result when dislocation move. So each and every lines, every terms you have to understand, you have to imagine this. It is like an abstract concept. It is. So we have slip between crystal plane. So slip between the crystal planes in the physics we studied. Imagine you have simple cubic structure. One point is 0, 0, 0, one corner, we are saying 0, 0, 0. We have 1, 1, 1, one more opposite corner. If we join all three, 1, x1, y1 and z1, x-axis we have 1, we can mark point 1. Y-axis 1 unit, we can take one more point. Z-axis 1 more point. And finally we'll get, if we join all those 3 points, so then it will become plane. That will be 1, 1, 1 plane. That I am not going in detail because those things are studied in physics. So those are referred as a crystal planes. If there are some photos, if you are not able to imagine, I'll add and I'll put it in the next class. But you have to remember what is crystal plane. Result when dislocation move. So a slip between crystal plane result when dislocation move. Sometimes during the rainy season, there's a, so this floor is wet, you may slip also. That you can imagine. In the similar way, when materials are subject to external loading, so the complete crystal or the grain will slip or group of the atoms will move. The same thing is showing here. Slip between crystal plane. Crystal plane, you are familiar, 1, 1, 1 plane. 1, 1 plane means x-axis 1, x-axis already you marked, y-axis you have marked, and z-axis you have marked. And get the distance, unit distance in x-axis, y-axis, and z-axis, you will get 3 points. If you join those 3 points, but then it will become triangle. So it will look like a one triangular plane. So now slipping takes place at a particular crystallographic plane. I am talking about the crystallographic plane. All planes, the slipping may not take place. Only at certain crystallographic plane, the slipping takes place. Those planes are referred as slip planes. Now, produce permanent deformation or plastic deformation. That concept already you studied. So when load is applied beyond yield strength or yield load of the material or beyond the elastic limit, the material undergo plastic deformation. The one more name used for the plastic deformation is the permanent deformation. This is a permanent deformation. Now you are talking about the zinc. So zinc is having HCP crystalline structure. This is a before deformation. This is after deformation. So don't think that it is like your tensile test specimen. This is one crystal. I'm talking about the one crystal of the zinc. The crystal size may be 1 mm or 0.1 mm. Don't think that you have the zinc rod of certain length. Imagine, don't think that the zinc rod of 1 feet length, you are applying load, so then you will get deformed like this. It is not like this. You are considering one crystal. The size of the crystal may be size of the grain or size of the crystal may be 0.1 mm diameter or 0.2 mm diameter. We are assume that the crystal is almost like a cylindrical shape. It's only for the analysis purpose. Strictly speaking, grain or crystals are not cylindrical shape. There may be irregular shape, but still you are assuming that the grain or crystals are cylindrical shape. So once you assume it is a cylindrical shape, then derivation will be easy, and assumption we can go ahead with many assumptions. So you are applying load. So once it is applied load, it undergoes elastic deformation. So now whenever it undergoes elastic or plastic deformation, some slip planes will be created here. So like playing cards, if you push the some one card will slip over the another card. You can imagine, no? In the similar way, there are different crystallographic plane in the material, in the grain. Those crystallographic plane, when it is subject to loading, the complete slipping will take place along the crystallographic plane or favorable crystallographic plane. You can imagine 100 number of planes or few hundred or 50 number of planes. All 50 planes will not undergo deformation. Only few planes may undergo this slipping takes place or slips. Like when we are moving the vehicle, only some wheel may slip. So all will make ships also, because there is a plane surface between the tire and road surface. But there are some favorable conditions where shipping takes place. In the similar way, in a crystallographic structure, there are n number of planes. In all planes, it will not fail. Only one plane, the shipping takes place, or it undergo plastic deformation. One thing you have to remember, it is not you are assuming that the grain is in cylindrical form. Within the cylindrical, we can assume number of inclined plane. There are n number of inclined plane. Out of n number of inclined plane, there is a one plane which is more favorable for slipping. Imagine imagine there are 100 people in a group. Out of 100 people, one man maybe slips from the 100 in the group because of some reason. So more favorable planes, we are saying more favorable plane is favorable for the slipping. Not all plane will slip, only one or two plane may slip, and because of the slipping, it undergo plastic deformation. We can see the produce permanent or plastic deformation. This is the zinc grain. It is before deformation. Once it is subject to elastic loading, tensile loading, now n number of slip planes are takes place. Don't think that this total length is around 1 feet, similar to your tensile test specimen. It is not 1 feet. It is hardly, it may be few micron or 1 mm or 2 mm. This one is schematic diagram. We are talking about the linear defect, dislocation. So now how much amount the material undergoes deformation? You studied about the vector. So imagine you are moving from BMSIT towards Hebbal. There is one direction. Still, in the similar way, you are moving from BMSIT to Dodpur right direction. The distance may be same. Distance may be only, let it be around 5 kilometers on both the side. But direction you have to say. So one is towards south and one more is direction is towards north. So for that, we require, in the similar way, the atoms will moving either in different directions, or group of the atom will move in the different direction with certain magnitude. To describe this movement of the atoms, we require some vector that shows both magnitude as well as the direction. Those vectors are referred as a Burger's vector. That Burger vector is referred as a B. Don't think that it is a burger, what you regularly eat. That is not a burger. This is a scientist name. Hence, it is referred as a Burger's vector. How much amount of distance this one plane of atoms moved is expressed in terms of Burger vector B. So one line of atom, dislocation line, so one line of atom is moving by small amount, let it be 1.1 mm along north direction or south direction, west direction, whatever it may be, then it is a dislocation line. I think now we can understand here. Is it photo is visible? Photo? PPT is visible, this sketch? Yes or no?
Yes, sir.
Okay. So now these are the atoms. We have one line of atom here. This is one line of atom. It's perpendicular. Imagine it is perpendicular to wall. So here, this is one row of atom, this is one more, this is one row of atom, this is one line of atom, one more line of atom. Those atoms are arranged perpendicular to the wall. So here like that, 1, 2, this is one plane of atom. So this is a second plane of atom. This is third plane of atom, fourth plane of atom, fifth, sixth, 7. There are 7 plane of atom here. All atoms, the left 3 and right 3, those are the perfect. But if we consider the one more plane of atom, the one more plane of atom is middle atom here. We can see here this is a middle atom, one more plane of atom. So this is not complete. Only half is existing. Only half of the plane of atom is existing. Then it is referred to the edge dislocation line. This is represented by this line because only top there is a plane of atoms, bottom there is no plane of atom, hence it is referred by inverted T. So inverted T is nothing but edge dislocation. Only upper half there is a one plane of atom, the lower half one half plane is missing. Half plane of atoms are missing, then such type of defects are referred as the edge dislocation. I hope you can understand. Or we can say that there is one more way. There is a extra plane of atom in grain or in crystal. We have 6 plane of atom. These 6 plane of atom cannot be referred as extra plane. Only there is a half extra plane of atom because there is a one half of the extra plane of atom. Hence, it is a comes as imperfection. If all if we have this plane is also continuous, then it is not referred as imperfection. Only half of the plane of atoms here above this slip line. This line is referred as slip line. Then it is referred as a edge dislocation. The simple sketches are available. You can see here. You have to understand one more plane also. That is referred as slip plane. Imagine imagine the playing of the cards. If you push the card from the top as well as bottom, so between the card will slip. So that plane is that where exactly slips, that particular plane is referred as a slip plane. Suppose you are walking in wet floor, suddenly you may slip. The top surface of the floor is slipping plane, and bottom surface of the chapel is also slipping plane. You can imagine like that one. We have bottom surface, the bottom is floor, the top we are human being. The whole body is not a slip plane, or whole floor is not a slip plane. Only top surface of the plane is slip plane, and bottom surface of the chapel or shoe or slip plane. In the similar way, you can see here we have this is a crystal. So don't think that it is a steel metal of a size of 10 inch by 10 inch. It is not a steel metal or metal rod. It is single crystal or single grain. You are referring this as single crystal or single grain. So when it is subject to tensile loading, the top portion of the atoms are trying to move in the forward direction. Bottom portion of the atoms are trying to move in the reverse direction. So between the top plane and bottom plane, here understanding this, especially this understanding this, you have to concentrate more. You have to study day to day. You have to practice these sketches. Also, simple sketches are available in Punish textbook. But to understand concept, I am showing some 3D sketches. Between top plane and bottom plane, there is a plane. That plane is referred as a slip plane. Your dislocation is nothing but a defect. It moves along the slip plane from this point to this point. We can see here. This is original. It is a perfect crystal or perfect grain. When it is subject to loading, so this top portion of the crystal or grain will try to move in the forward direction. I hope you understand. But there is one plane which separates upper half of the crystal and lower half of the crystal. That plane is referred as a slip plane. Any difficulties here? If you have any doubt, you can clarify. There is a two topic here. One is edge dislocation. One more is screw dislocation. You should be able to differentiate between what is edge dislocation and screw dislocation. Once you understand, you can explain. I have some more photos. No need to write all those photos in the test or exam. Only one schematic diagram, if you write, that is sufficient. But you have to understand. You have to write. You have to explain the exam or even for the test. You may write only one diagram. If there is no doubts, clarification, I go for the next four. Now you can observe here. Dislocation motion requires successive bumping of a half plane of atom from left to right. This is successive bumping of a half plane of atom. So when you're saying half plane of atom, even if you're referring to any local books also, even Panish also. So once you say half plane means what you should understand what is half plane. The half plane in this case is this top portion. We have slip plane. Above the slip plane, there is a half plane. Below the slip plane, there is a one more half, bottom half of the half. But this top as well as bottom of the crystal are separated by slip plane. Dislocation motion requires successive bumping of a plane of atom from left to right. What is successive bumping or movement? Suppose this extra plane of atom should move to this particular position, because it will not move forward. You understood, no? So imagine you are standing in front of the wall in the room number, let it be 201. You want to move to 202. So you want to move from the back wall, because back wall is fixed now. You cannot move. But suppose you want to move to the room number 201 to 202, you have to push the wall here. You can see here, this is a wall. It's a plane of atom. So you have to push the wall. So once you push the wall, there is a half of the wall will move towards forward. This half of the wall will comes here. This half of the half plane will comes here. This half plane will goes and moves in the forward direction. Now this half plane is now here. It comes here. Once it comes, then once again some amount of work is applied or load is applied. Then it will push this three atoms to the right side. This will be this atom. So then the same process continues. Suppose if there is a one extra plane of atom here, you can see here, this is a one extra plane of atom. So this distance is not 1 centimeter. You have to remember, this distance is not 1 centimeter. That distance is one atomic diameter. It may be 1 angstrom or 2 angstrom. You can imagine there's a 1 angstrom or 2 angstrom. So now you can see this is one more schematic sketch. We have top half plane. This is one crystal. So within the crystal or within the solid body crystal, so there is a one plane. This plane is referred to crystallographic plane or crystal plane. We have dotted line. This dotted line is crystal plane. So once load is applied, the top portion of the crystal is moving forward along the crystal plane or slip plane. Bottom portion of the crystal will start moving towards left again along the crystal line or this slip plane. This is also referred to slip plane. So these are now you can see atomic view of edge dislocation motion from left to right as a crystal is sheared. The crystal is sheared is nothing but, so now you can see a shearing. We have one single crystal. This particular crystal is sheared off. Sheared. So that means it moved forward. That is nothing but shearing. So now in a similar way, so here each and every atoms are moved by the same distance. In some cases, instead of applying tensile load or compressive load, if you apply torsion load, the twisting moment. So now once it is applied twisting moment, this portion is elongated. Only this particular portion is elongated, and this is the top of the plane. This is bottom half of the plane. Do you have a doubt? Any doubt about the top half and bottom half? It's a one crystal. You are assuming that crystal is in a cubical in nature. The intersection point. This is one intersection point. This is one more intersection point. On those intersection point, you are assuming that there is a one atom. Instead of showing different circle, they have shown it by the regular rectangle. This is the regular square or rectangle. So now this is the top portion of the crystal. This is the bottom portion of the crystal. This whole crystal will try to slip. about the slip plane. You can see this is the about the slip plane. If this particular plane or line of motion is moved by 1 mm, then your Berger vector is also 1 mm. This is one more sketch. Edge or screw or mixed dislocation. I think can you imagine? Imagine you have one duster on your table. If edges of the dusters are parallel to the edges of the table, if you move like this, then it will become screw dislocation. Just you are pushing the duster. But we can hold the duster, we can rotate the duster, then it is after screw dislocation. One is linear movement in the case of edge dislocation. In the edge dislocation, atoms will move linearly. In the screw dislocation, you know how screw, when you tighten the screw, how you are applying the load. It is a torsion load. So when it is subject to torsion loading, so now you can see here, all atoms are not moved by same distance. Some atoms are moved by a small distance. Some atoms are moved by. Hello? Just 1 minute. So some atoms are moved by a small distance. Some atoms are moved by a bigger distance because you are rotating. Imagine you have a paper, a book. You are rotating about one fixed point. At that particular fixed point, the movement of that particular point is 0. But other corner, the remaining 3 corners, some points are moved by 10 mm, some points are moved by 15 mm. So like that. So there is a edge dislocation. In the case of edge dislocation, it is subject to tensile or compressive loading. So we have one more experiment also. By using universal testing machine, you can apply tensile or compressive loading. There is one more experiment in material testing laboratory. That is about a torsional testing machine. In torsional testing machine, you are applying twisting moment. You are twisting the shaft. You are not applying any tensile or compression load. When material is twisted or metal is twisted, metal consists of number of grinds. From the beginning, I am telling metal consists of number of grinds. Hence, it is referred as a poly grind. You are not analyzing the complete the metal. We have poly grind. So you are taking out one grind from the poly grind and you are analyzing one particular grind. This particular grind is, you are assuming that it is a cube. It is a cubical shape or this is a prism like shape. You understood that. We have metal. Metal consists of metals consist of n number of grains or polygrain material. Out of polygrain material, you are not studying the all material together, how each and every grain rotates or undergo deformation. So you are selecting only one material. You are checking how the deformation takes place, how the material will be. So in our college, we may have more than 3,500 students. Suppose if you want to get some opinion, so you are taking only one student. You're not going for taking opinion of all students. There's like a random sampling. In the later stage, you're going to study. So you are taking randomly one crystal. You are assuming that one crystal. Now you should understand. You have to imagine what is crystal. Crystal consists of n number of the unit cell. So now you are taking one crystal or one grain. You are applying torsion load. When it is subject to torsion load, the movement of the atoms are not uniform. So here Berger vector magnitude may be 10 unit. Here Berger vector magnitude may be 15 unit or it may be 5 units. Here somewhere the Berger vector magnitude is only few micron. That is method is referred as a screw dislocation. So now this is the edge. This is edge dislocation. There is a one extra plane of atom. You can see here. This is a one extra plane of atom in the case of edge dislocation. In the screw dislocation, only some corner of your grind is rotated. It is moved. There is an angular movement for the small portion of the. In simple way, there is an angular motion for the small portion of the crystal. Don't say materials or workpiece or metals. You have to refer with respect to crystal. You can say that, and in the edge configuration, the axis of perpendicular plane, Berger vector is parallel. Here it is perpendicular. That comes here. This is the Berger vector. This is the extra plane of atom. It is the edge dislocation. This is the extra plane of atoms. These photos may not be available in the textbooks, taken from the downloaded from the different sources. Imagine you have the crystal or grain. In the crystal or grain, only one extra plane of atom. Extra plane of atom, and this extra plane of atom causes deformation. You can see here that this deformation, how much it is rotated, how much it is moved, is given by Burger vector B. This is Burger vector B. When there is no defect, when suppose if you are moving from this point to this point, you can find out what is the distance moved along with the direction. If there is a defect, what is the distance moved when there is a defect? Just best imagine you are moving from BMS82 to Hebbal flyover. Imagine, so there is road is clear. We can find out what is the distance moved by the vehicle from BMS82 to Hebbal. That means there is no imperfection, there is no defect, there is no traffic jam, no traffic deviation. If there is a traffic deviation, some roads are blocked, then again we are reaching to the same position Hebbal from BMS80, let it be some Vidyaranapura road or some other road, but again we are reaching the destination point like Hebbal, but distance traveled will be more. How much distance, extra distance is followed, taken to reach the same location, that distance is measured in terms of Burger vector. In simple way, what is the distance traveled when there is no defect? That is that we can get it. So when there is a defect, what is the distance traveled? So whenever there is a difference of that distance is referred as Burger vector. That will be if there is no defect, to move from this particular point to moving like this, you are coming back to the same point. You can see here, no defect here. You are moving starting from here, you are moving to the right, then finally you are reaching the same. That will be, it will move by 10 unit distance. But here there is in the crystal there is a defect. Suppose one road is closed, so you are moving from here, then you are taking the different path, then you are moving the straight line, then here there is maybe some road blockage. To avoid road blockage, then you are taking one more turn, you are reaching here. The initially it is moved by here, if there is no defect, it is moved by 10 unit. Because of the defect here, it is moved by, instead of 10, it may be 12 mm. The 10 minus 12, that is 2 mm, is the magnitude of the Burger vector. So now it is a dislocation line. Similar type of diagram may be available in the book. You can better to write this. In the case of screw dislocation, this is the Burger vector. The direction, it shows the direction. The top half of the plane is moving towards right in the angular manner. You have to understand. You have bottom half plane. There is one more top half plane. I hope this is your slip plane. There is a flat surface. Slip plane, you can imagine when you are walking in a wet floor. What is slip plane? The top surface of the floor is slip plane, and bottom surface of your chappal or shoe, it is again a slip plane. So now you may not move straight, because whenever slipping you may turn also. Then it is referred as a screw dislocation. Here, instead of slipping and moving in the exactly forward direction, it is slightly rotated. You can see here the Burger vector magnitude may be very less here, but here the Burger vector magnitude is more here. A similar sketch is given. You have a complete crystal. This is one crystal, and it is moved by small distance, small edge. No, you can see here. This is the edge. Hence, it is referred as the edge. But here, the top portion is rotated. Then it is referred as a screw dislocation. There is a rotation here, angular rotation. But between top plane and bottom plane, there is a one plane. This is shaded, dark shaded. I think you can see the dark shaded plane. That is nothing but a slip plane. This dark shaded plane is slip plane. Here also you can say the complete slipping takes place along the slip plane. We may slip on the floor along the slip plane only, on the top surface of the floor and bottom surface of your slipper or chappal. That is nothing but a slip plane. Here also, that is in the macroscopic level. I have given an example. But here this size, I don't think that it is a metal block. It is, this size may be around 0.1 mm height, 0.2 mm length, and width may be around 0.01 mm. That is the size. It is a one, you are taking only one grain. You are assuming that grain is having some prisms like this prism-like shape. Those who are not entered your USN number, please enter your USN number. Just I am showing some syllabus. You should know what is happening. Just another 5 minutes. I am discussing about what are the topics you are studying in second module, as well as third module, not third, fourth module, so that second module and fourth module will be there for your test. Just I am opening the syllabus. Wait. I hope syllabus is visible now. Okay.
Yes, sir.
Syllabus. So I am not getting the PPT of the syllabus. Just I'll read what are the things you are studying in module 2 and module 4. So module 2 and module 4 will be there for your test. Module 4 is on composite material. So there is no much fundamental you are studying in the composite material. Then, but module 2 required more time. What I'll do is I'll give some introduction to the module 2, some portion I'll cover. Then I'll finish the composite material. Composite material will not take much time. So when you come to composite material, at least you can start preparing for your second test also. So composite material is something interesting, not like what you're studying in the first module and second module and third module or material science fundamental, but composite material is the application of the material science. There you're talking about the composite material, definition of the composite material, classification of the composite material, types of matrix material, types of reinforcement material. Then one more is metal matrix composite material. The metal is the major element. Ceramic matrix composite. The ceramic material is the material. And one more is polymer matrix composite, where polymer is the major element in the composite material. Then particulate reinforced and fiber reinforced composite as a special type of composite. The particles are added to the main MMCs or PMCs. Then fundamental of production of composite, how composites are produced, fundamentals. Characterization of the composite, how we can find out the properties of the composite material, how to get the microstructure. Constitutive relationship of the composite material. That means once you know, like a steel, imagine you have the beam, steel beam, building beams. We have steel is also there and also the concrete is also there. If you know the strength of the concrete and strength of the steel, so once the beam is fabricated by steel as well as concrete, what is the strength of the complete RCC beam? So that we required some constitutive relationship. Instead of testing the beam, what is the strength? We know the properties of steel is known, properties of the concrete is also known, that can be tested in the lab. And finally, we can estimate or predict the what is the properties or strength of the beam, final beam. The determination of the composite property from individual component property. Same thing what you are discussing. We know the properties of steel. We know the properties of the concrete. From that, how we can find out the property of the final beam. Then hybrid composite, when there is more than one material, two materials, then it is about the hybrid composite. Application of the composite, the numericals on determining properties of the composite. There are two derivations, and based on the derivation, there are some problems are there. So that is the module 4. Module 4 is easy. So, and I have all PPT. I'll give the notes also. Module 4, you can refer Panish also, but still I have written handwritten notes. You can refer at your choice, but I'll put the notes in the Google process. That is the module 4. Then module 2. Module 2 has huge. Module 2, 4 is complete, is there for your third test, the second test. Module 4 is complete. Module 4 is there for your second test. Then our case study material, case study question as well as innovative questions will comes under module 4 only, because it is applied. We cannot ask any case studies and innovative questions from module 2. And module 2, first part of the module 2 is failure criteria, fatigue creep, and one more is fracture. The second part of the module comes under phase diagram. What you're discussing now, those are the fundamentals required for the phase diagram. So then types of alloys already you are discussed. Solid solution already you are discussed. Factors affecting the solid solution, Hume-Rothery rules, and again phase diagrams you are not discussed. Different types of systems are there: eutectoid system, intermediate phases, then iron carbon diagram, non-equilibrium cooling, and homogeneous homogenization, and iron carbon diagram, effect of alloying element in steel, common alloying steel. That part you already finished for your first test. That second module, last portion already you are going for the test: common alloy steel, the stainless steel, tool steel, the specification steel, then cast irons. So those second some part of the module 2 already have covered for your case studies and innovative questions. The major part involved is the phase diagram. For module 3, the fundamentals required for the module 3 heat treatment is the phase diagram. That's why it's giving more importance for the second part of the module. Finish the second part of the module 2. Already you have finished steels and cast iron finished. Then you have to go for the case studies. Now you have started with, already you have finished 2 classes for second part of your module 2. Final conclusion is, for second test, the module 4 complete unit is there, the composite material, and module 2, whatever the portion you are covering in the module 2, that will be there for your second test. Some already 25% of the portion is covered, steels and cast iron. That part already you are given for the case study question for the first test. Okay, if there is no clarification or doubts, or you can, I'll leave the session. Any doubt? No. Once again, I'll discuss the module 2, because I'm discussing of talking about the module 2. At least you should know what are the things you are going to study in the module 2. Next class, once again, I'll describe what are the topics you are studying in module 2. Overall picture I'll give you. First 5 minutes or 10 minutes I'll give the overall picture of the module 2. Then I'll continue with the phase diagram. Today's topic I'm going to continue. Okay, thank you. We'll meet tomorrow.